Under normal conditions, gases do not discharge through them, that is, electric current do not pass through gases under normal conditions. But when the pressure is very less and when the applied potential is very large, then gases conduct electric current. So, the discharge of gases can be observed using a glass tube, which we call as discharge tube. Such a discharge tube is shown in the figure here. It consists of a long tube of about 40 centimeters in length and about 4 centimeters in diameter. And two electrodes are placed inside the glass tube, one cathode and another is anode. The cathode is connected to the negative terminal and the anode is connected to the positive terminal of external power supply. And we are using a vacuum pump using which we can change the pressure inside the glass tube. The pressure can be adjusted according to our requirement. Now, it is observed that when the applied potential is very large, say 15,000 to 20,000 volts, and when the pressure is very less, about 0.01 millimeters of mercury, then a dark space fills the entire tube, and that is what we call Crookes dark space. The pressure should be about 0.01 mm of mercury, and the applied potential should be about 15,000 to 20,000 volts. In such case, the entire tube is filled with a dark space which we call Crookes dark space, and it is also observed that there is a fluorescent glow behind the wall of the anode, and this glow indicates that there is a stream of rays which are moving from cathode and reaching the anode. These rays are called cathode rays. These rays are called cathode rays because they are emerging from cathode, and later they are named as electrons. These cathode rays have certain properties, like they travel in straight lines and they have certain momentum and energy. They can be deflected by electric and magnetic fields, and the direction of their deflection indicates that they are negatively charged particles. Later they are named as electrons, and it is also observed that the charge to mass ratio of these particles remains constant irrespective of the gas inside the tube. In this way we can study the discharge of gases, and this particular experiment led to the invention of electron. J.J. Thomson experiment. This experiment is used to determine E by m of an electron, that is charge to mass ratio of an electron. It is also known as specific charge. Specific charge means ratio of charge of electron to the mass of electron, and that can be determined using this experiment. The apparatus consists of a discharge tube which consists of a cathode and an anode. A large potential difference can be applied between them, and we can see discharge of electrons through gases. Next, these electrons which are emitted by the cathode are accelerated towards the anode. This accelerated beam of electron enters into a region where an electric field can be applied. We are using two parallel plates P and Q which are perfectly parallel to each other, and the electron beam passes through them. And also there is an arrangement wherein a magnetic field can be applied perpendicular to the plane of this board in this direction. If the electric field is like this in this direction, then magnetic field is applied in a direction perpendicular to the electric field. Both electric field and magnetic field are perpendicular to each other, and such fields are known as crossed fields. Next, the electron beam strikes a fluorescent screen, and on that it produces a glow with which you can identify the position of the electron beam. Now, in the absence of any electric field or magnetic field between the two plates, the cathode rays which are emitted in the discharge tube strikes at the midpoint on the fluorescent screen. You can see it with a glow. Now, when an electric field is applied, the electron beam or cathode rays gets deflected. You can see the deflected beam at a different location on the screen. Now, a magnetic field is applied in a direction perpendicular to the electric field, and the magnetic field is so adjusted that the electric force and magnetic force applied on the electron beam are exactly opposite and equal in magnitude. As the electron beam passes through the plates, we are applying an electric field and magnetic field which are perpendicular to each other, and we will adjust the fields in such a way that the electric force applied on the electron beam and the magnetic field applied on them will be exactly equal in magnitude but opposite in direction, so that these forces will get cancelled and the net force acting on the electron beam will be 0. Once again, the deflected beam comes back to its original position, that is the middle point of the fluorescent screen. At this point, we can conclude that the forces due to magnetic and electric forces are equal, and accordingly we can calculate the value of E by m of an electron. First, when you are applying an electric potential to the electron, a work is done on that one. The work done due to this one is equal to EV. Here E stands for the charge of electron and V for electric potential, that is applied potential. This work done is used to increase the kinetic energy of the electron. Therefore, this work done can be equated to the kinetic energy of the electrons, that is 1 by 2 mv square. From that, we can write an expression for V square which is equal to 2 EV by m, or we can write expression for the velocity of the electron beam which is equal to square root of 2 EV by m. That is the expression for the velocity of the electron beam. Next, we also know that at this point we can cancel off the electric and magnetic forces by properly adjusting the fields. The electric force, let us say Fe, is given by EE. Here small letter e stands for charge of electron and capital E stands for the field strength, electric field strength. Next, the magnetic force is given by Fm, which is equal to EVB. In that, V stands for the velocity of the electron and B for the magnetic induction which is applied to the electron beam. Now, we know that these two forces are equal, so that the deflection, there is no deflection in the electron beam. In such case, we can equate this EE and then EVB. From that, we can calculate the velocity as E by B. E on both sides will get cancelled and you are left with V equal to E by B. Let us say this to be equation number 2. From 1 and 2, we can equate them because both represent the velocity of the electron. Therefore, square root of 2 EV by m is equal to E by B. You can observe this one. This is equation number 1 for the velocity of the electron, and this is equation number 2, again the velocity of electron. We have equated both of them. Squaring both sides, you will get 2 EV by m equal to E by B, E square by B square. We are squaring the equation on both sides. From that, I can write expression for E by m which is equal to E square divided by 2VB square. That gives you the required expression for the specific charge of electron. Specific charge means ratio of charge to the mass of electron, that is given by that expression. If you look at that equation, this is the electric field strength and this is the magnetic induction. and V stands for the electric potential that is applied to the cathode rays. Next, substituting all these values, it was found out that E by M value comes out to be 1.76 multiplied by 10 power 11 coulomb per kg. This is the value of E by M of an electron, which is equal to 1.76 into 10 power 11 coulomb per kg. That's E by M of an electron, which can be determined using J.J. Thomson experiment. Milliken's oil drop experiment. This experiment is used to determine the charge of an electron. The apparatus consists of a chamber in which two plates are kept. Like the two plates are perfectly parallel to each other, they are metallic plates and they are separated by some distance. Now the upper plate has a narrow hole drilled into it so that oil drops can fall through them. Next, we are having a window on one side of the chamber using which light can be sent into the chamber. We are having a source of light, from that light is sent into the chamber and the region between the two metal plates can be properly illuminated, and the space between them can be viewed through a telescope which is placed on the other side of the chamber. The telescope has a micrometer arrangement so that you can measure the distances. Now a heavy oil is used in the experiment. That heavy oil can be split into small droplets using a device called atomizer. It splits the oil, heavy oil, into very small drops, and these small drops of oil are made to fall on the upper plate, and through the hole on the upper plate they will slowly fall down into the region between the two plates. They fall due to gravitational force. Now during the process of spraying of the oil, these oil drops get charged, and the charged oil drops are falling between these two plates under the force of gravity. Here these oil drops experiences a number of forces. Force due to gravity is acting downwards, whereas viscous force due to air and force of buoyancy are acting in the upward direction. The resultant of all these forces gives a constant velocity to the oil drops, and this velocity is known as terminal velocity, represented by Vt. Now that terminal velocity can be determined using the telescope and micrometer arrangement, and also using a stopwatch. We will measure the time taken for the oil drop to travel a particular distance, and the distance can be measured using the micrometer arrangement. From that we can calculate the terminal velocity of the oil drop. After that, see, the two plates, metallic plates A and B, can be connected to an external power supply so that we can apply an electric field between those two metal plates. Once the electric field is applied, the oil drops experiences an electric force. Now the oil drops tend to fall down due to gravity. At the same time, since they are experiencing a net upward force due to electric field, there are a number of forces acting on the oil drop. The electric force which is acting in the upward direction, and also force of buoyancy will be acting in the upward direction. The gravity is acting downwards. Due to these forces, the oil drop acquires a net constant velocity. That constant velocity can be represented with VE, that is velocity of the oil drop when an electric field is applied between the plates. Now knowing these two values, we can determine the charge on the oil drop using this expression. Q is equal to 6 pi eta multiplied by Vt plus Ve divided by E. By knowing these two velocities, we can determine the charge on the oil drop, that is the velocity without the application of the electric field, which is known as terminal velocity Vt. After that, the velocity acquired by the oil drop when the electric field is applied, that is Ve. By knowing these two values, we can determine the charge on the oil drop using this expression. Q is equal to 6 pi eta Vt plus Ve divided by E whole multiplied by 9 eta Vt divided by 2 into rho minus rho dash G whole power 1 by 2. That is the expression. In this, eta stands for viscosity of the air and E is the electric field that is applied. Next we have rho and rho dash which are the density of air and density of oil drop respectively. G is acceleration due to gravity. Using that one, we can calculate the charge on the oil drop. Next, it is observed that the charge in various cases, it is observed that it is an integral multiple of an elementary charge. That is, any amount of charge that is on the oil drop can be written like this, NE. Here, N stands for an integer and E for the elementary charge. This elementary charge is nothing but charge of electron. It was determined as the charge of electron equal to 1.6 into 10 power minus 19 coulomb. So, using this experiment we can determine the charge of electron as this much, 1.6 into 10 power minus 19 coulomb. Another conclusions which we can take from the experiment is charge is quantized, in the sense any amount of charge must be an integral multiple of an elementary charge. This elementary charge is nothing but charge of electron which is given by this much. And further, in the earlier case we have also determined E by m value for an electron, that is specific charge, which comes out to be 1.76 into 10 power 11 coulomb per kg. This is the specific charge for an electron and this one is the charge of electron. By knowing these two values, we can calculate the mass of electron and it comes out to be 9.1 into 10 power minus 31 kg. So, using this experiment, we can also determine the mass of electron.